So this is Dominic, and he's going to talk about quantum common causes and coherent control. So,
thank you. Is this? Yes. So as is traditional, thank you to the organisers. You will never get tired of being thanked because this is an amazing conference. And because we may run out of time at the end, I was going to do this at the end, but because it's important, I'll do it at the beginning. It is Juani's birthday. We should all sing happy birthday. So I'm going to take the first 1 minute of my talk to sing happy birthday. So my voice is breaking, so you'll have to all join in. So 1, 2, 3. Happy birthday. Those were 3 announcements. We'll do the birthday bumps later. Okay, so changing gear. It is great to be here at Q10 to talk not just about who we are, but what we do and how it all works together. So today I am going to be talking about something I have never talked about before. You're all getting results hot off the press. This was a completely new slide set. That just shows how much I care about this conference. So I'm going to talk about what it means for one quantum system to cause a change in another quantum system, which sounds incredibly simple, but like most things in quantum mechanics, the questions are simple, and then you can spend your entire life getting confused about them and diving in. So let's dive in and get confused. So I'm going to basically be explaining how this diagram, which I've neatly coloured in the Q10 colours, explains to us. I wasn't able to get these colours into the actual diagram in the paper, so you'll see it's green if you look online. So I will explain how this enables us to have a framework in which we can understand quantum causality in a new way, and how hopefully this will help us understand what sort of quantum operations are possible, because causing one thing to happen based on another thing is kind of a definition of computation, although the computer scientists would tear their hair out at that. And say there's not enough lambda to calculate. But, you know, we all know that's what we're talking about. And so if we can get an idea of how quantum causation works, then we can get an idea of what we can do with it, and specifically how we can use it to information process. So what I'm talking about is essentially orthogonal to these two papers. So it's a line of research that started slightly aside of the first and continued in the second. So I'm using results from both of these to draw a conclusion that isn't in either of these papers, but you should definitely go and read the papers and cite them, not just because I'm on them. So what I am going to be talking about is this idea, as I said, what does it mean for one quantum system to cause something to happen, and how that computationally is what's known as an if statement. And if you're looking blank at that, you'll realize we don't have a general framework of that in quantum computing. So that's what I'm trying to talk about. And the first thing, if you do anything to do with causation in quantum mechanics, you have to reckon with is the Bell inequalities, specifically the CH-SH inequalities. So I'll go into what they tell us about how causation and specifically common causes act quantum mechanically. And then it's like eggs 4 ways, redefining quantum common cause 4 ways. So this is the results of the first paper, where we had basically 3.5 ways of defining what it means for one quantum system to act as the common cause of 2 others. And then how we can put this notion of a quantum if statement into that same framework, and then finally use that framework to get some really cool and really bizarre behavior coming out of it. And that sort of points us towards this understanding that if you understand what it means to coherently control an operation based on a quantum state, then a lot of our intuitions about certain areas of quantum Shannon theory seem to be destroyed. So I'm just trailing that. So the last bit is going to be really, really crazy results, and it's great because everything is in quantum mechanics. So to start off, what does it mean for one quantum system to cause a change in another system? So I might use terminology a bit loosely, say, one quantum system causing another. So I'm thinking in terms of quantum variables. And why should we care about this? So hopefully by the end of this talk, I will have convinced you that we should care about this. So first motivation is the foundational one. A lot of us want to understand this weird and wacky world of quantum mechanics, and the way quantum probabilities work is one of the few handles we've got. And so understanding what it means for causes to propagate will tell us a lot more about how quantum probabilities act. So classical probability theory is built around this thing called Reichenbach's principle. And here is one way of describing Reichenbach's principle. So no correlation without causation. And some of you may be sitting there going, hang on, wait, I was told correlation doesn't imply causation. What's going on here? And like all best things in life, there is an XKCD for that. So here we are. So correlation, of course, does not imply direct causation, but also, as all things in life, the hover text, the alt text of the XKCD is the important bit. So if you ever try and take a screenshot of the alt text, it's really difficult because you've got like 1 nanosecond before it goes away when you try and press the keys. But just for you, I did this. So I got the screenshot. There we are. So correlation doesn't imply causation, but it does waggle its eyebrows suggestively and gesture furtively whilst mouthing, look over there. And that is a brilliant summary of Reichenbach's principle. So Reichenbach's principle is, I thought of terming this talk suggestive waggling, but decided that would probably be considered, it might look bad on the schedule. So what Reichenbach's principle is saying is that if you've got a correlation, there is causation going on somewhere. But what the correlation does not imply causation means is you can't say that one of those variables directly causes the other. There's more complicated ways of looking at causation. So to do our suggestive waggling, so the various ways that you can be correlated classically. So if A is correlated with B, then causally we've got variable A, variable B, and either A can cause B, or else B can cause A, or else, and this is the important one that people often forget, and so try to say that, the number of turtles causes people to stop smoking because they're both correlated. A and B can have a common cause, C. And that's it, classically. Those are, any combination of those is how you can relate variables to each other and how variables can cause changes in other variables. And these things are called directed acyclic graphs. They underlie the whole of modern classical probability theory. A lot of AI and machine learning is built on people manipulating them. And the way you define where you put those arrows in a DAG is through notions of conditional independence. They really underlie it. So if you have a full set of conditional independence relations between variables, then you can get the causation DAG out of it. And what I mean by conditional independence is things like this. So this symbol here, we read this as A is independent of B given C. So that's a statement of conditional independence. It actually turns out to be much more powerful than absolute independence. And that says that when you have this condition of conditional independence, your probability of A and B given C factorizes into a probability of A given C and a probability of B given C. And we can think about this, we can sort of read that expression as, if you already know C, then knowing A tells you nothing more about B. So the idea here would be that C would be a complete common cause of A and B. That's the terminology that we're using. And so you can think of these objects, so these conditional probabilities here, you can think of those like channels of causal influence. So there's a causal influence going from A to C and from B to C. And rather famously, quantum probabilities don't work like this, or don't immediately work like this. And we'll see that when we go on to looking at Bell inequalities. Very briefly, don't worry, I'm not going to rederive the Bell inequalities or anything like that. So that's sort of the first reason why we want to look at these notions of common cause, because they underpin classical probability diagrams. And if we want to view, as quite a lot of people do, want to view quantum mechanics as an extension of classical probability theory, then how do we extend that diagrammatic language to quantum mechanics? How can we use this notion of conditional independence and DAGs and Bayes networks and all of these things that the AI and machine learning crowd really love? How can we do quantum that? By the way, if you're ever writing a grant proposal and you can say quantum machine learning in it, then do that, because that's, if you try, see if you can get was it Bitcoin in there as well. This is a challenge. Okay, so that's motivation one. Motivation two, we want to understand what different types of quantum information processing are possible and how they operate, and specifically what type of controlled operations, so 2 or more qubit gates, are possible. So the connection with this notion of a common cause is when one system or variable is causing an operation to be done or not done on another system, that is known as a controlled operation. And controlled operations they underpin classical information processing and quantum information processing. So if you don't have controlled operations, then you can't get entangled qubits, and you can't get you can't have multi-qubit gates if you don't have controlled operations. And the one that everyone knows and loves is the C0. So this is a controlled NOT operation. For those of you who don't know, we'll look at it in detail in a bit, but it's the way you read this is, if the controlled qubit is in the 0 state, then you do nothing to the target qubit. And if the control qubit is in the 1 state, then you do a bit flip, so an X operator on the target qubit. So the state of the control qubit is causing either nothing to happen or a bit flip to happen on the target qubit. Another place where we get controlled operations more generally is these controlled unitaries that pop up in the phase estimation algorithms. So you may recognize, some of you, this particular diagram, which I have very neatly managed to steal without attribution, so I feel terrible about that. I think I got that off Wikipedia, so I'll fess up to that now. So here we've got, so this is a control, and then it's controlling this. I mean, don't worry exactly what it is, but it's looking like it's saying, well, we need this control of an arbitrary unitary, so isn't that done? Should I just go and sit down? Well, if any of you have looked at these things, you'll know what we actually need to do is decompose that. So that is a convenient fiction, as a lot of circuit notation and quantum computing terminology is. It's a convenient fiction that's hiding an awful lot of detail. Here is some of the detail. So you decompose this controlled unitary into lots of controlled 1 and 2 qubit gates, but you can't do arbitrary 1 and 2 qubit controlled unitaries. You need to decompose them. This is for the single unitaries into a library set of gates. Here it's rotation gates and Hadamard's. So that's where what controlled unitaries look like. They're basically standing in for this box. And if you don't have the decomposition of a controlled unitary, then you can't implement it. Final place where we have this notion of quantum control going on. Sorry, there is a thing in optics, I think, called quantum control. And so if anybody deals with that and I say quantum control, I'm sorry. I'm meaning this. So technically we're calling it quantum coherent control. You know, the good terminology has always been taken, but just for time I may say quantum control, and I'm meaning this. So the quantum switch is a type of quantum control. Who has come across the quantum switch? Excellent. There are so few places where that would be a majority show of hands, so another reason to like Q10. Yes. So this is essentially setting up indefinite causal order. So this is saying, based on the state of the control qubit that's coming in here, if it's 0, then you do the order C0, then C1. These are operations. And if the control qubit is 1, then you do it in the other way round, C1, then C0. So if you shove your control qubit in a superposed state, then you can get a superposition of doing both C0, then C1, and doing C1, then C0. So we'll talk a bit about the switch later. So that's sort of a third framework that we've got so far. But we don't have a general framework for what would be a quantum if statement. We don't have, as we do classically, a sort of quantum computing wrapper for this idea of, if something is the case, do one thing. If it's not the case, do another. And being able to do that in the superposition. So being able to be in a superposition of that condition being triggered and being not triggered. So classically, you get diagrams like this for, you know, here's the condition, and if the condition is true, you do this, and if it's false, you do that, and then you go on. We don't have a framework that looks like that yet. You will have by the end of the talk, hopefully. And if anybody is sitting there going, but wait, hang on, what about that paper? I will come to that. So there is famously a no-go paper that sounds like we shouldn't be able to do this, but I will show how we get around that particular one. So this is the idea that we're aiming towards, is this kind of framework for quantum if statements. And I'm just keeping an eye on the time. Okay. All right, well, you've all seen the next few slides anyway. So I said famously, quantum probabilities don't act like classical probabilities, and the place that we see that the most, particularly to do with conditional independences, is in the Bell inequalities. So this is one statement of the Bell inequalities that you can see it as, even when direct causation is ruled out subluminally, so not faster than light, then quantum probabilities still don't factorize. So remember, in the conditional independence definition, you have that factorization of probabilities. That's what we don't get in the Bell inequalities, even when they're far enough apart that light signals can't get between the two of them. And we think, so in that situation, that's exactly the situation classically, where you'd say, well, they have a common cause. You know, in the Bell situation, you create an entangled pair. That's the action of the common cause, and then you send, you know, one half off here and one half off here. I think it was Delft. They just sent it down to the other side of the city, and that's the common cause generating A and B, and you're then looking at the correlations of A and B, and the problem is that they don't factorize. And the way that this is shown, that I'll go into, uses a classical a standard classical causal model, which in the kind of history of quantum foundations, we've called a hidden variable model. But basically, the hidden variable model is people looking at quantum mechanics and stamping their feet and saying, "No, God damn it, it really is classical probabilities underneath the hood," you know, and they try and work out what that would imply. And so, what you do here is you try and recreate quantum probabilities using a classical causal model, and then obviously famously we see that they don't fit. And also famously, every time you give a talk about the Bell inequalities, it is entirely possible that somebody misunderstands what you're going to say, and obviously there's always an XKCD for everything. So here, this one. So this is essentially saying that as soon as you start talking about Bell inequalities, someone somewhere, maybe on the other side of the world, thinks, aha, right, so we can communicate faster than light. So I am not talking about faster than light communication. And in fact, I'm not going to talk about most of the Bell inequalities, because I'm really interested in the causal model underpinning them. So what is the causal model that we use to derive the Bell inequalities and then say, oh, well, the world doesn't work like that because we've violated Bell inequalities experimentally? What? Get out. I've been called out. Okay, moving on. That was more of a comment than a question. So to set up, so looking at the way that the Bell inequalities, and here specifically the CHSH inequalities, set up this classical causal model. So we have our hidden variables, lambda. So those of you who've not come across hidden variables, you can imagine these as like actual classical systems that are out there that we can't see, and they're just behaving in a really weird way that we call quantum mechanics. And we have a probability density over the hidden variables row, and we're saying that when you've got two systems that have been caused by a third system, then the only thing that can go between them to cause those correlations is the hidden variables. And so when you're measuring something, you have, for an observable A, you've got this function, which is a function of the measurement settings and the hidden variables, so we can accommodate contextuality in this. And then the expected value of the measurement is you sum up over the space of hidden variables the probability density and these measurement functions. And that's all very classical. So you'll find bits of classical probability that deal with these probability density functions in exactly the same way. And then when we're looking at joint measurements, then we have, say, a joint measurement of A and B, the expected values of these given measurement settings, little a and little b. So we've got our function of big A and our function of big B, and then our probability density over hidden variables integrated over the space of hidden variables. So that's what treating this all classically would give us. And this is a factorization of probabilities. So famously, if you derive a Bell inequality using factorization of probabilities, then that's the thing that the real world will violate. So somehow we're not getting factorization of probabilities. And so if you were reading this classically, you would say, well, even spatially separated quantum systems, if they're correlated, they appear not to be conditionally independent. Because something like this would be the exact analog of the conditional independence condition. So can we get a better conditional independence condition is the question there. So this is just to reiterate why this is a conditional independence condition here, because we've got this idea that are hidden variables must be the common cause of whatever's going on and whatever's going on at B, or at least must be the common cause of the correlations of what's happening between them. So there's always multiple responses when quantum mechanics throws up something weird and wonderful. So there's a few responses we can make to the issues of Bell violations. These are not mutually exclusive, by the way. So we can reject the idea that one measurement gives you one outcome. So this is moving to a multiple outcome local realism, and that's the many worlds interpretation. We can say there are somehow superluminal causal influences that are propagating through the universe, and we can't use them to communicate, but we can know they're there because they're the things that violate Bell inequalities, which is a bit like saying I give up as a physicist. So in the spirit of not giving up and trying to, let's take a hammer to some of our assumptions, well, can we redefine what it means for there to be a common cause quantum mechanically? So the factorization of probabilities related to hidden variables, obviously, maybe that's the problem. Maybe we just need a better understanding of what it means for two variables to be correlated through a common cause quantum mechanically, and it's going to be something to do with, you're able to do this in superposition because the causal object can be in more than one state at once quantum mechanically. And this was first proposed by Wood and Speckens, and that's the open published paper. Which is why I don't have the archive version on it, and that is what I'm going to be talking about next. So, are there any questions? Just because I want to drink some water, so are there any questions? I'm not going to look at Ravi because he's trying to make me laugh. Failing. Okay, so let's have our eggs four ways. Let's try and come up with a better way of defining common cause quantum mechanically. Hopefully by now I have persuaded you this is really important. So, what sort of thing do we want out of a quantum Reichenbach principle? So the quantum Reichenbach principle will be two quantum systems are correlated, but we're not going to throw our hands in the air and go, oh, there's just some kind of superluminal signaling happening in the background. We're going to go, no, we've got a causal picture. A causes B if they're spatiotemporally co-located. And if two things are correlated, then there's either direct causal influence between them, or else they have in their causal past a common cause. So Reichenbach's principle. So what do we need quantum mechanically for that? So here's a nice little picture. You'll notice I have very neatly, just to confuse you all or to keep you awake, I had A and B up here before. I've now got B and C up there, and A is the common cause. So B and C can be entangled. And one of the first things we learn about entanglement theory is that means our density matrices don't factorize. But we can have situations where A is still a common cause of B and C. So like in the Bell situation, you can imagine B and C are two halves of a Bell pair, and A is that same pair, just they're together. You are correct. Yes. Sorry, that was well done. That was just to see whether you're awake. One person's awake. Right, now you're all totally confused, and I'm confused. This is complete common confusion. So, step one. In taking the general recipe of doing the quantum version of anything is take your ingredients and make them quantum. So what's our ingredients in looking at conditional independence and conditional probability? Well, the first thing is these things like probability of B given A, and I really do mean B and A here. So probability of B given A. Now, classically, that's a perfectly well-defined thing. It's a matrix. But we don't have a density matrix in standard quantum theory that is the equivalent of this thing, because what this is it is, yeah, I've just given it away. So so that thing is, how do you figure out what the probability of something in the future is based on something in the past? Well, quantum mechanically, we have channels, but we also have an ability, quantum mechanically, to turn channels into states. So I'm just going to say this in a little bit of detail in case you've not come across it, because it can get a little bit gnarly. So quantum mechanically, we have a differentiation between things that happen at the same time and things that happen over time. So states, quantum states like ρ, are normally, in standard formalism, defined on variables all at the same time, and then the states evolve over time under the operation of unitary operators, or you can think of them as evolving under the operation of channels. So states at a single time, channels over time. But you can take a channel operator and turn it into like a pseudo state. It's not an actual state and will give you weird probabilities, but you can think of it, so this is called the Choi-Jamalkowski isomorphism. Don't ask me which way round is which. There's kind of two types and it gets very confusing. But you can think of it like if you've got a Bell state and you do the channel operation on one half of that Bell state, then the state that you get out is the channel state. So we have this kind of fiction, but it's a way of turning a channel into a thing that looks like a density matrix. So we're going to use that. So here is the channel, so this curly epsilon thing. So the channel from A to B, so this channel here. And what that normally means when you've got a channel operator is you can... Well done. This is the problem with new slide sets. I'm trying to keep a mental note. I owe you 2 beer, right? I do this with my students when I'm teaching. I give them like the carambars when they tell me there's a problem in the slides, because you should never just take for granted what someone up the stage is talking about. Always question. So yes, that is row B. So the output state is the input state times the channel operator, and we can turn that channel operator using the Choi-Jamalkowski isomorphism. If you know it, here it is. If you don't worry about it. And so we've got this thing that looks like a density matrix, looks like a conditional density matrix. And it has the kind of properties that we would want. It lives, again, don't worry too much about this. That's like the transpose of the Hilbert space of A. It's technical. So it lives on the joint Hilbert space of A and B. And we can do things with that channel state. So for instance, this really is right. We can get the output state B out by taking the partial trace over A of the channel state and the input state. So one thing, just briefly, you can ask yourself is, great, we've got this thing that looks like classical conditional probabilities. Then what about joint states? So classically, you can define the joint state of 2 variables. It doesn't matter whether they're at the same time or different times. Quantum mechanically, well, do we have a way of doing that here with our conditional state? To which I would say, great question, even though I said it myself. And here's a paper I happen to have, just because I'm first author on it. I think it's great. So go and read that if you want to look about states over time. But here I'm just going to look at the quantum equivalence of the conditional states. So that's for joint states. So what we're going to do is, as well as looking at this situation where we've got arrows over time, we've got the conditional state of B given A, and we'll have another one that's the conditional state of C given A. We're also going to bring in things that look like hidden variables, but they're not really. And we're going to say that sometimes the operations, the channels that take us from A to B and C are not unitary. And what that means is that there's some extra causal influence coming from outside, and we're calling that lambda B and lambda C. So that's channel dilation, Stein-spring dilation, if you have come across that. But again, if you don't know those phrases, don't worry about it. So what we did in the first of those papers that I showed you, which I'm not going to prove because there's no way enough time, is two theorems that give what I would call is 3.5 different ways of defining common cause quantum mechanically. Here they are. I am going to talk through them, don't worry. And I'm also aware they're too small for you to read right now. So what we have is, the first one is in words. So we're talking about the joint state of rho BC given A, and saying it's compatible with A being the complete common cause of BC. So that's, if you like, the wordy definition, the half definition of complete common cause. And then these three conditions in the theorems are the three different ways in which we can unpack that quantum mechanically. So let's expand them out. So the first one is the closest to what the old classical conditional probabilities factorizing looks like, but it's actually, interestingly, turns out to be the least interesting condition, as in the one that gives you the least knowledge out of it. It's just matrix multiplication. Yeah. So you need to tensor with some identities. So have a look in the paper. But so we've got a first notion that you factorize the channel states, so that BC given A factorizes into one channel from A to B and one from A to C. But yeah, like I said, we don't really get much out of that. So let's move on to the others. Here we go. And the first one is about mutual information. So again, if you know what that is, then the equations will make sense. If you don't, then I'll say in words. So this is saying that so the mutual information is the information that one system will have in the other, and this is exactly the condition that if you know the common cause, if you know A, then B will tell you nothing more about C. So this is the mutual information of C in B given A is 0. And that turned out to be a rather neat way of seeing that part of the classical intuition. And we found that each of these conditions kind of picked up one aspect of the classical intuitions. So classically, they're all contained in the same expression. Quantum mechanically, they seem to be parceled out into different expressions. And then finally, now, this is the really important one. So this is my favorite. So, and I would say this is probably the most quantum, but it's also the one that looks the most immediately inaccessible, aka intimidating, probably. So what this is saying is that when A is the complete common cause of B and C, then you can decompose the Hilbert space of A into, if you like, a left-hand side and a right-hand side. And the left-hand side is the only thing that is causing things to happen on B, and the right-hand side is the only thing that's causing things to happen on C. And this enables you to decompose your density matrix. Now, this sum is important. I'm going to explain a lot more on the next slide, but just to say this sum is important because it's saying the density matrices factorize, but they factorize not across the whole space, but across this direct sum space. So let's see what this actually means. So what this is saying is that our Hilbert space factorizes as a direct sum based on some variable I, and that variable is going to be really, really important, and we'll talk about it for most of the rest of the talk. So I is indexing a load of subspaces, the Hilbert space, that we're going to sum up to get the main Hilbert space. And so on each I, we can partition our causal variable A. So the Hilbert space of A partitions into a left-hand side and a right-hand side. And then there is some channel state from the left-hand side of A to B. And there is some channel state from the right-hand side of A to B, to C, sorry. And we can take the tensor product of those two channel states and get a channel state for that value A, for that value I. And then what we do to find the channel state for the whole thing is we sum up over the I's. And that, the fact that we can do that with our density, with our channel state density matrices, is telling us that the Hilbert space factorizes like this. Now, the first time I saw this, I was just like, well, I have no idea what that means. So if you're in that situation, that's fine. And what I'm going to do is now show physically how we can understand this kind of structure, because this is the structure that corresponds most closely to controlling operations happening on other variables. So one way you can think about this I is as a control setting. So you can imagine a dial with lots of different values of I. And for every value of I, we have this factorization of the Hilbert spaces. And we've got this thing that looks very much like classical conditional independence going on. So keep that I in mind. And we can have a nice diagram like this. So here you can see very much the idea that this I is kind of controlling this decomposition. And yeah, we can have the dilated diagram as well. Okay, moving on swiftly, I'm now going to tie this in to a framework for coherently controlling quantum operations, and hopefully this will give you much more of a sense of what does that horrible complicated diagram actually cash out to physically. So I'm going to do physics and show you an actual experimental implementation of it, although I'm a theorist, so I'm just going to draw diagrams rather than show you actual experiments. So the type of controlled operation we all know and love is the C0. This is the simplest. As I said, it's if the input state is 0, then you do nothing, and if the input state is 1, then you do a bit flip on the target. And we can write it as a unitary matrix like this, and write it in various other ways. Ooh, that's an interesting transition. So one thing to note first of all is that the C0, quantum mechanically, it's much more complicated than just a not operation with something done to it. It can set up entanglement, it can propagate phase information from the target to the control. So there's more going on here than just a sense of, well, either do a not operation or don't. A coherently controlled not operation is a different thing altogether. So can we get a framework that does that sort of thing for any quantum operation. And now remember I said right at the beginning that some of you might be sitting there going, but what about that paper? So, can we swap in an arbitrary operation? Here is the but. Quantum circuits cannot control unknown operations. Oh, are we sad kittens sitting in bowls? You know, is that it? Do we go and have coffee earlier? Fear not, no. We can be happy cats. There is a loophole. Hurrah! We like loopholes in quantum mechanics. Where is the loophole? The loophole is there. Quantum circuits can't control unknown arbitrary unitaries. But actually, when we were starting to do this work, and we were all just there going, but hang on, doesn't Chaslav's paper say we can't do this? I went into the paper, and the loophole is in the paper. They explicitly say there is one situation where you can quantum mechanically control an arbitrary unitary, and that's in an interferometer. So what's going on here, and I will speed up, what's going on here is you have an input state through a partial beam splitter, and this, of course, so this is a polarizing beam splitter. So what it's going to do is if you're in the 0 state, it'll transmit. If you're in the 1 state, bumps you up here. And then you've got the unitary that is operating on your qubit in one arm. That is that is quantum control of an arbitrary unitary, and they very explicitly say that. And it actually, they've very nicely pointed out how it gets around their no-go theorem, and I won't go into the technicalities of it, but what we want from it is that it gets around their no-go theorem because it gives you a certain structure to the overall unitary. So the whole thing is implementing a unitary, not just this thing here. And it has this structure. And to know that you have that structure for your overall unitary is enough to get around their no-go. So hurrah, we've threaded that needle. Now we start cooking with gas with this particular structure of the unitary. So let's look at this in a bit more detail. Well, that is, if you go into Matrix Mechanics 101, that is a direct sum. So I'm flipping between this version of the identity and this version because I took this from the paper and this is my own LaTeX. And so what we've got is the direct sum of an identity and a unitary, and we can unpack that a little bit more. So a basis for the control qubit is 0 and 1. So this is 0, does nothing, 1, it does the unitary. And that's the matrix element that is relative to the Krauss operator for the 0 state of the control and that of the 1 state of the control. So we can actually write that unitary in this form. So we've got the Krauss operator for 0 and the operation that you do when it's 0, Krauss operator for 1 and the operation that you do when it's 1, and then you're adding up. And so we can rather suggestively talk about a Hilbert space for the control and the target, and it factorizes because we've got the tensor product, and this is relative to the 0 state of the control qubit. And do you see what it is yet? And here we have one for the control and the target that is relative to the 1 state, and we have a direct sum structure of our Hilbert spaces there. And you can squint at that, and we've got this for a C0. So there is the identity and there is the not operation in a control not. And we can do the same decomposition there. And we squint and go, does that look familiar? Hopefully this should look slightly familiar from 10 minutes ago to everybody. Some people are nodding, some people are awake. The rest of you just want to get to coffee. Okay, so it is, voila, our common cause condition number 4. So what we have is we have factorized, so the factorization into subspaces for our quantum controlled unitary is each of these subspaces. I said these i's were going to be important. You should listen to me. Each of these i's is this control state of the control qubit. So what we've got is a very specific Hilbert space structure that gives us a decomposition of the density matrices for the channels that is related to, for each state that you have of the control qubit, you do one operation, and these are different operations. And that decomposition of the control qubit into different states that you're going to control relative to is what drives this structure. And that structure is the one way we can get around Chaslaw's no-go theorem for being able to do this in the first place. So it's a rather neat, the threads came from about 3 different places, which is one way that you can tell in science that what you're doing is probably right, or at least interesting, or at least wrong in interesting ways. How much time do I? 5 minutes, okay. So, condition 4 is more general, just to say, so here I'm looking at, if you've got 0, do nothing. If you have 1, do a unitary operation. Condition 4 actually would be the equivalent of this. So it's saying if you're in 0, do 1 unitary, and if you're in 1, do another. And we can, we can have a diagram that will lead in very neatly into the next section like this. So this is an interferometer, so this is a polarizing beam splitter, and if you're in the 0 state, then you're going to be transmitted, so you're going to do U0, and if you're in the 1 state, you're going to do U1. So this, we propose as the quantum framework for an if statement. So based on the decomposition of the control qubit into various i's, relative to each I, so your i's are your conditional here, and we can have multiple superposed versions of this diagram. So you can think of this diagram as for each node I, you've got another diagram. And so in actual fact, what we've got is that diagram upside down. That's just to help you view it. So now, in the last 5 minutes, I'm going to talk about some work that we did looking at this idea that you can coherently control quantum operations, and what type of behavior do you get out of that. And so these are some initial results of how this idea of let's coherently control a channel changes what we think that channel is. And very specifically, so are there any channel properties that change when you coherently control it? So if you just operate the channel, then it acts in one way, but if you operate it in a superposition of the controlling variable, then do we get something else? And yes, we have one of those situations, because I wouldn't ask the question if I didn't. So this particular story, which I'll go through very briefly, starts with the quantum switch and this particular paper, which essentially said if you put in 2 copies of a single depolarizing channel into the quantum switch, then you get out something that will actually enable the transmission of information. So a depolarizing channel should wipe out every piece of quantum and classical information that you put down it. But what they found is if you plug 2 versions of the same one into the quantum switch, then the output state has a non-trivial dependence on the input state. And so when this paper came out, the general consensus, when people were talking about it, was, oh, this is weird stuff that comes about with indefinite causal order. And we looked at it and scratched our head and went, hang on a second, we don't think that's anything to do with indefinite causal order. And so that's the quantum switch. What we did was discover that you can get exactly the same behavior using just coherent control of channels. So no indefinite causal order at all. So this is the Ebler-Ehrlich and Kiribella results. So they've got the quantum switch, and it's very neatly, almost like our coherent control, but it's got this extra channel that's doing the superposition of causal ordering. And this was their output state. So there's two, C0 and C1 are the same depolarizing channel, and the output state still has a dependence on the input state. So that means there's some information going down that channel. So we said, all right, let's just get rid of this bit. Ditch that. We're just going to coherently control. So if it's 0, we're going to do C1. If it's 1, we're going to do if it's 0, we're going to do C0. If it's 1, we're going to do C1. And let's, see what we get out. And so here's, just in detail here, is how we did the depolarizing channel. So it's the collection of unitaries that give us the identity out there, and we can sum up over all of them, and our output state has a dependence on our input state here. So what that T is a collection of all of the unitaries that are giving us the depolarizing channel, and relative to the off-diagonal elements of the control, then we have information transfer. So this also very neatly shows you, if that control is classical, we only have this term here. So we have no information transfer under classical control, but under quantum coherent control, two depolarizing channels can transmit information. There's more. So what more there is, again, just speeding up, you can tell what the purification of your depolarizing channel is. The amount of information that you can get out depends on how that depolarizing channel was created, which about blows every single intuition about depolarizing channels out of the water, because it should be just erasing all information. So what on earth is going on? Well, we can bring in our nice diagrams. So first of all, conclusion 1. Whenever you are talking about coherent control of channels, you have to talk about their purification if they're not already unitary. And secondly, we need to update our intuitions about what channels are, what information is transmitted when we use them with coherent control. And these diagrams actually help us, because they're showing, so this is the purification. So this is information transmission about the purification is going through the channel and getting to the output. So you can start to see why that would be there. And so hopefully it's less intuitively crazy. And finally, if you've got a channel and you think you're secure when you're transmitting information down it, then you really have to rerun those security proofs under coherent control, because you may be able to extract extra information out from them. And so finally, there's some summary. Quantum coherent control is different, and we can now define it, and it uses the framework of quantum common causes. And I will stop there.
Thank you. We have time for one question, and we have one announcement as well. So, questions? Okay, there.
Hi, thanks for the great talk. So maybe this is very embarrassing, and it's been one of the first 3 ways of defining the common cause, but this condition, the funny one with direct sum and stuff, that reminded me very much of this condition for 3-partite states to satisfy the strong subadditivity condition with equality. Was that one of the first 3 things you said? Oh, I don't know.
No.
Okay, great. Because, I mean, do you know that it's this Patrick Hayden paper and stuff, like the structure of states satisfying the strong subadditivity
Yeah,
with
the,
equality.
con-
Is
the
that the same?
connection to strong subadditivity is something we want to look at because it's obviously there, but we haven't found,
Exactly, because it's kind of related to this existence of PETs, recovery maps, which might be actually interesting in terms of thinking of the common cause as something that you could sort of
we should talk.
recover or something. Yeah.
So let's thank Dominic again.